Hello, welcome to the section where we talk about the control pipeline of the source code. As you see, the control pipeline is basically consists of two components. One is the soccer trajectories component. Basically, what this does is it publishes fixed trajectories, like a kick, like a fixed trajectory that we have hard coded. And then there's the soccer pi control. Basically what this one does, it does all the uh, walking trajectories, basically walking and various kinds of walking and rotating the head. Perhaps Jonathan has already explained how the head rotates. Um, so these are the two components here, soccer trajectories. We can start with a simpler one. Simpler one is this soccer trajectories. It only has a single file called soccer trajectories, and this is the main runner of that file. Basically what this component does is it listens to a topic called command, and that command will go to this run trajectory, and it will check that command that if it's contained in this trajectory. So different commands are different for different models of robots. For the sake of simplicity, BES1 has a get up. There's like these are the three commands here: get up, front, back, side, and there are some right kicks. And mostly, you don't. If you have a right kick, you don't need to do a left kick. Um, Let me just run the code for you. Oh, yeah. So to be able to configure these commands, you want to go to here, each of these guys here, and then you want to look at it as a CSV file, and then we have the exact time and the exact motor angle of that time step. So for example, at time 0.5, the motor angles are like this, and there's a comment saying this is the stance, and then it starts leaning to the right, then lifts this leg up, and then does kick, and then step to balance. So you can see like these are the time steps. So this one kick takes 8 seconds, and let's look at this node here. So what it does, it subscribes from the topic called command and the state, and when it's finished, it will publish an action complete. So all I need to do is go here and publish a topic command. Just keep pressing tab. I need to find the trajectory name. Let's call the trajectory name right kick. Close this camera. Let's see if it does anything or not. And then as you can see, it goes and does that right click. So I can modify these trajectories and then run them in simulation if I need to. Yeah, this part is very simple. Next we go on to the more complicated part, soccer pie control. As you can see, this also receives a go rather than a command from the strategy. And for example, in the strategy code, how this works is that go to robot control 3D. The publisher is the Go publisher. The Go publisher is run in the set navigation position function, and so basically you just need to in this strategy code just call this function robot.set navigation position. It will publish the movement for the robot. Okay, we can start here. So we can start with main. This is where the entry point of the code. So there's two things, a navigator and a navigator ROS. Navigator, anything that has an underscore ROS means we're doing it in ROS. Anything that doesn't have it means we're doing it in PyBullet. So for example, if I go on one of these tests, you can see that the navigator is using a navigator rather than navigator ROS, but in main it's using navigator ROS. Most of this code is documented, but like there's stuff like initialize, set pose, get pose. You can read this up about all of this in the documentation. But the main thing here is this one while loop over here in the run loop. What this while loop does is it receives that go that is given by the soccer strategy somewhere around here. This new go is not self.go, and new go is created by this callback function that is subscribing to the strategy. A go is basically a 3D pose. Another way you can simply just send the go. You can also simply just send the go by using 2D navigation go here. That is another way you can do so. You can see the green point is there. However, I don't think it's working at the moment. Yeah, and yeah, you can see this navigation go is the same topic that it's subscribing to. So one way you can just simply test out the navigation is to allow the robot to navigate to the center, and then kill the soccer strategy component, and then just play around with this navigation go thing. So yeah, what happens after that? So in this navigator, we have this object called a Soccerbot. It's probably, yeah, it's created here, a Soccerbot ROS or Soccerbot, depending on whether you're running in ROS or not ROS. And basically, for example, in this run function, it basically uses the robot path that is stored in the Soccerbot. So what is the robot path? So let me just run this, show you what exactly happens here by putting up debugging this here. Okay. So when it calls set pose, it's just setting the pose of the robot. Never mind. Um, Now this is the function set go. It will run this call this function create path to go. This create path to go is run inside the Soccerbot function, and what it does is it first takes the go you have and add the torso height, because the go is based on the height of the movement of the torso rather than the body. Um, and then after that it checks if you want to use calibration. The calibration function is here. It basically takes like it has the main function is here. It takes a position x, y, theta, and it returns another position x, y, theta that is calibrated based on the robot's friction. So you can actually run calibration. Like what it does is it goes sends it to go to a few set of distances, 1 meter, 2 meter, for example, and then see how much it actually goes to, and then uses that and creates a function that tells you how much it actually goes to versus how much it wants to go to, and then uses that for calibration. I'll show you that in a second. And then after the calibration, it takes that fixed pose and creates a path robot. Path robot is this right here. Path robot inherits from path torso, which then inherits from path foot, which inherits from path. So think of it. Path is like a path between the 2 feet from the starting position to the end position. And then after this path is determined, we create the pass foot, which is like 2 sets of like 2 mm, arch, like sets of arcs for the feet to from the starting position to the end. And then after that it creates the path of the torso, which is the location of the center of the heart of the robot. Sometimes you want the torso you do want the torso to go a little bit left and right when it's moving. So you want the torso to sway a little bit from left to right when it's walking, otherwise it's gonna fall. Oh, by the way, also all the parameters are located on top of the class function. And then after path torso, everything gets wrapped up in this large function called path robot, which has one function, a nice function called show timing diagram, which shows the timing diagrams of the feet and torso. So I go here, it initializes, it does some stuff. I won't go into too much detail about the code, but if you're interested, you can read up about it. For example, it's done, and then we have something called a robot Odom path, which is because we have given it a path from, we have this calibration thing. We go from, for example, 0 meters to 2 meters, but we tell it to go from 0 to 2 meters, but in reality it goes from 0 to 1 meter. But the Odom does not, still thinks it's going from 0 to 2 meters. So that we want to give the odometry from 0 to 1 meters. So one of them creates a path from the pose to the calibrated position and one of them to the finished position. And then basically, because of these two different paths, we actually send commands according to robot path, but we send odometry estimates based on robot Odom path. So what does this path look like? For example, there's a nice useful function here, walker dot Soccerbot dot robot path dot show. I do want to disable this because just give me a second. What is it called again? Yeah, just disable show plots into a window when you do it now. After the set go function, you go Soccerbot. Seems like it's not working, so I'm gonna just do it like this. There we go. Now that's not in the plot window, I can actually drag and visualize the different paths of the feet. It's very slow. Okay, it's upside down now. But anyways, you can see that the feet move a little bit outwards, and then this line over here is the path of the torso. The torso is fairly straight, I guess. But in the real robot, the torso might need to swing a bit left and right. So to adjust these parameters in the real robot and in simulation, you can go here in config. The sim means in the simulation. Here's the information about the calibration. Try not to touch that. And this is the parameters. All of these are ROS params, and they'll also be read in the test function. After that, it'll run the walk, and it's not showing because I turned display to false. So to show it, I turn display to true, and then I can see that the feet, okay, so there are basically three different paths that all you care about. The torso, the feet, and the feet, these are the ones subject to configuration. The rest is done through inverse kinematics. Let me just show you where that inverse kinematics function is. So under Soccerbot, we have this function. We have this function called inverse kinematics right foot and inverse kinematics left foot. Right foot, I mean, basically only inverse kinematics right foot is done. Inverse kinematics left foot is just the flipped version of inverse kinematics right foot. So all of this math is already done for you. And you can read up about the description here. Yeah, so first these three paths are created, and then it does the inverse kinematics from the torso, which is the blue arrowed one, versus the feet, for both feet. So if I close this here, you can see that it will start walking like this. Okay, one thing to mention, there's two types of paths. Under paths, I already talked about these files, the paths, torso, feet, robot, and that. Oh, another I forgot to show you. If you run that show timing diagram, it will create a timing diagram. What does that look like? Okay, basically what it's supposed to look like is it shows a bunch of at what time does the feet go where. Yeah. I think I have to just put block equals true. And then maybe it'll work. There you go. As you can see, the first diagram is the footstep ratio. The second one is the foot body pose. And then we have the X position. X is forward. Position of X or right and body. Z position. So you can see the first step's a bit smaller, and then these are these different steps. Sometimes you might see the word crotch. It just means torso. It's just unfortunate choice of words. And then distance between the torso and the feet. So one thing, to run the calibration, you can click on this. Ross Foss, okay. So it is basically running a calibration here. And then after it runs the calibration, it will create a calibration file, update these files, X, Y, and A2. So this is the formula for the calibration parameters, assuming that the forward movement is a quadratic function, and the rotational thing, oh sorry, it is a quadratic, and after a certain distance it becomes linear, and for rotation it's just a linear function. What have I not? Okay, now we talked about navigator Rus, path, robots, torso. So the remaining thing to talk about is the path section. So what is this? Each path contains multiple path sections. At the moment, only one path section is created. A path section is just like a short part of a section of a path, and there's two types. One is a short path. A short path is basically a move, turn, turn, move, turn kind of path, where you might see in some of the pretty common in some of the 2D leagues for robotics. And there's the Bezier path, which does a nice curved path. So, and then there's one condition to determine whether it is a Bezier or short path. And this function is short path. Yeah, so it checks if it's mostly it's most of the time it's a short path, unless it's a simple forward movement. Then it's kind of weird to do a short path, and it's more efficient to do a Bezier path. Then it will use a Bezier path. But when the ball is like behind the robot and it needs to do some weird movement, then it's a short path. Maybe some other paths will be created later on in the future of this code. So in addition to test walk 1, 2, 3, we have some tests called like test turn in place, test small movement. So a small movement is gives a short path, basically. So for example, you can see that the robot does a little turn, turn, move, turn, basically. Turn, move, turn. And that is what we have, a short path. Yeah, that's pretty much it about for the explanation for the control code. Oh yes, I forgot the hardware pipeline. So what does the robot publish after it after it does the control code? Well, the main publisher is the angles of the robot. So for example, in Soccerbot ROS, there's a function called publish angles, which basically takes the configuration plus the configuration offset and sends it to ROS. Okay, what is the configuration offset? I forgot to mention. If you go to navigator, so before it starts moving, it does this little PID thing where it tries to stabilize itself to it tries to stabilize itself before it starts walking. While it's walking, it does another set of PID to try to keep the robot stable while it's walking. And then when it's completed walking, it does the same set of stabilization. Let me try to find it. Okay, so the function is apply IMU feedback standing. And then there's also apply IMU feedback, which just implies walking. So these two functions, you can see this is the walking PID using the PID class found in the Soccer Common. And it takes what it does is the feedback, usually right at the moment, just uses the left and right arms as feedback, and for standing also uses the left and right legs. These were just picked arbitrarily. And then this feedback creates this thing called a configuration offset, which is added to configuration, which is the one created by the path creator. to try to keep the robot more stable. Um, yeah. Uh, okay, now to talk about the hardware component. Soccerbot Ross publishes this at this topic. Publish on motor called joint command. What does joint command look like? Okay, so there's also joint command and joint state. Joint states is what the simulation or the actual motors is reporting as the angles, and joint commands is what we're sending to the robot. So according to the simulation, all the motors are at 0 position. Joint command, right now nothing is publishing. What listens to that? Well, there's a thing called the Weebots bridge. Weebots bridge lives inside Soccer Weebots source bridge Weebots, and what this does basically, it takes these angles that are sent by sent by the robot, and sends it to the Weebots. I'm sure Jonathan might have explained to you in the previous video. If it does not, it gets sent to Soccer hardware on the real robot, where we have a bunch of functions here. I think we can leave this out for another video because it's another set of complications to explain the Soccer hardware code. So yeah, I think we'll end right here. Thank you for listening to this tutorial, and if you have any questions and doubts, please message the software support channel in the Discord.